Hey everyone, welcome back to The Explainer. I am absolutely thrilled to have you here today, my fellow focused learners, because we are kicking off a brand new series, Binary Aperiodicity. This is part one, and we're going to be exploring the absolute hard limits of digital reality. We're talking about the strict mathematical walls that dictate exactly how our computers interpret the physical world, and honestly, why they can never, ever do it perfectly. Now, I want to start things off with a bit of a core existential conflict. How do we fit infinity into a microchip? Because if you think about it, our reality, the sights, the sounds around us, the flow of time itself, it's this infinite, continuous wave. But our machines? Well, they only speak in finite ones and zeros. So how in the world do we bridge that gap? How do you take something entirely boundless and squeeze it into a tiny, finite little box? Okay, let's dive into this. Here is our roadmap for today's explainer. We'll start by unpacking the problem of infinity, then move right into the necessity of quantization. From there, we're going to tackle the math behind it all with rate distortion theory, visualize the geometry of compression, and finally, look at how we actually bound that data loss. All right, starting off with section one, the problem of infinity, the clash between reality and computation. So, the fundamental issue we run into here is that perfectly representing any arbitrary real number literally requires an infinite number of bits. If you want absolute precision, you need infinite storage space. And last time I checked, our hard drives definitely have limits. You can see it right here. On one side, we have continuous reality, analog, infinite precision, moving in natural, smooth waveforms. On the other side, finite representation, our digital world made of discrete bits and periodic binary sequences. Because a finite machine is trying to represent a continuous random variable, it can never achieve perfect fidelity. We are always dealing with an approximation. And look, we can't just mathematically cheat our way out of this either. If we look at the Turing machine limit, specifically through Chaitin's theorem from our sources, we learn something fascinating about computationally random sequences. Chaitin essentially proved that a computationally random sequence cannot be produced by a Turing machine if the machine's description is shorter than the sequence itself. If you try to map an infinite, totally unpredictable, continuous reality onto a finite computational tape, you're simply going to run out of room. There's just no cheating infinity. Now, to actually process this information, computers rely on something called automatable semiosis. Basically, this means splitting our continuous world into discrete, manageable parts. We use meaning symbols to hold values, that's our data, and action symbols to define operations, that's our code. But here is the big catch. To actually function in a physical electronic substrate, this whole architecture has to run on completely regular, time-stepped transitions. It can't flow smoothly like a river. It has to tick, rigidly, like a clock. Which brings us to section two, the necessity of quantization, snapping reality to a grid. So the crucial point is that because of these finite limits and the need for those ticking, time-step transitions, we are mathematically forced to throw information away. Let's ground this with a real-world example from music production. Think about a real human drummer. Their performance is full of organic microtiming and slight expressive jitter. That is continuous reality. But when you record that drummer into a digital audio workstation, the software enforces what's called empirical isochrony. It takes those fluid, human musical events and abruptly aligns them to a rigid, predefined rhythmic grid. It literally snaps the human feel to a mathematically perfect aperiodic binary sequence. And that brings us to our formal definition. Quantization is the mathematical process of discarding information to snap continuous analog reality onto a discrete, finite grid. It's the primary tool we use to artificially force this infinite physical world to fit inside the confines of a microchip. Basically, to make it fit, we have to throw something away. Let's move on to section 3, rate distortion theory explained, the math of lossy compression. Okay, so if we absolutely must quantize, and if we must discard information, we need a mathematical framework to optimize exactly what it is we're throwing out. Enter Claude Shannon's foundational concept, rate distortion theory. It defines the minimal data rate required to communicate a source without exceeding a tolerable expected distortion. If quantization is the tool we use, rate distortion theory is the mathematical rulebook governing how efficiently we're allowed to use it. Now, what's really interesting about this slide is how it visualizes that constant, unavoidable mathematical sacrifice. If you want pristine, high fidelity, you are going to need a very high data rate. But if you want high compression, meaning a tiny, easily downloadable file size, you are going to get high distortion. You literally experience this exact mathematical compromise every single time you stream a compressed MP3 on your phone or wait for a blocky JPEG image to load on a website. It is the systematic sacrifice of source entropy. Actually, before we get back into the heavy math, here's a pretty surprising, kind of ironic fact for you. While digital systems are entirely focused on mathematically optimizing this distortion, international copyright law actually has its own version of it. The Berne Convention, which is the oldest international copyright treaty, includes moral rights specifically designed to protect an author's honor from artistic distortion or mutilation. So, whether you're an algorithm compressing an image file or a human artist painting a canvas, avoiding unwanted distortion is clearly a universal struggle. All right, back to the architecture. Section 4, the geometry of compression. Why joint descriptions win. I really love this slightly humorous quote from the source material. It is simpler to describe an elephant and a chicken with one description than to describe each alone. Now, why does this actually matter for computers? Well, it matters because in high-dimensional space, independent problems do not have independent solutions. Describing things together is mathematically way more efficient. To break down that elephant and chicken analogy a bit more, if you try to map data independently using plain rectangular grid points, you end up wasting a massive amount of geometric space. It just doesn't pack well. But if you group data together into sequences, a process called vector quantization, you leverage the spherical concentration of high-dimensional volumes. You literally pack the space tighter and more efficiently, which gets you a much lower distortion for the exact same data rate. And this brilliantly illustrates how computers actually pull this off in practice, using processes like the Lloyd algorithm to find a good quantizer. They start by setting initial reconstruction points. Then they find the optimal Voronoi regions, which are basically just the nearest neighbors. Next, they recalculate the centroids of those regions, and then they iterate. It constantly repeats this loop, decreasing the expected distortion at each stage until it finally converges on a mathematical minimum. Finally, let's hit Section 5, bounding the data loss, the absolute thermodynamic limits. Now, I want you to focus here for a second because this is profound. How do we mathematically prove we've hit the absolute thermodynamic and informational rock bottom limits of compression? Well, the minimal rate of transmission is bounded by the mutual information between the original variable and its distorted output. We measure this discrepancy using highly specific mathematical tools called divergence functions, like the Kullback-Leibler divergence. This math allows us to calculate the absolute limit. It identifies the exact, precise point, the maximal distortion, where the transmission rate drops to zero and the output contains absolutely no information from the original source whatsoever. And what's wild is this limit applies to everything. The Shannon-Roa isomorphism proves that witness overlap in similarity search is mathematically equivalent to mutual information, meaning all retrieval methods, whether we're talking about simple Bloom filters or massively complex neural networks, they are all fundamentally bound by these exact same Shannon capacity limits. There is simply no algorithm, no matter how clever, that can beat this information theoretic barrier. To put a really concrete number on this for you, consider a Gaussian source, which is notoriously the most difficult type of source to encode. For a continuous Gaussian source, every single bit of description reduces the expected squared error distortion by a factor of 4. Or put another way, it reduces it to 0.25. So one single bit gives you a massive jump in clarity. But getting all the way to perfect, zero distortion, that would literally take an infinite number of bits. Let's move to how this builds into our modern AI era. We're currently going through a massive paradigm shift called coding for machines, or CFM. In this scenario, the target receiver isn't a human looking at a JPEG or listening to a song. The target is a deep neural network. We are taking these exact same rate distortion trade-offs and using them to compress latent representations solely for machine tasks, like object detection. We're bypassing human aesthetic perception entirely. The math hasn't changed at all, but the audience fundamentally has. Which leaves us with a really fascinating, honestly provocative thought to wrap up today. If all digital reality, every single photo, every sound wave, every massive data set, is ultimately a mathematically distorted, finite approximation of an infinite physical world, how do machines manage to learn, extract from meaning, and understand it anyway? Well, that is exactly what we are going to be covering in part 2 of the Binary Aperiodicity series. Stay focused, keep learning, and I will see you in the next explainer.